Trying a new method.
Use the vending machine method.
I'm telling you, like, go play the lottery tonight, right now.
Was that 3 for 1 or 3 for 2?
3 for 2.
3 for 2.
There's a room labeled vending machines, and I always thought it was just drinks.
3 for 1 would have been ridiculous.
Yeah, it's a vending machine.
I've had that on in a soda, like a soda.
Only did 2 because there was one that was basically 2 for 1 on the first one. They had to pay for it.
I think if one of them fell through and the other one was still in, it would have stopped.
Yeah, they literally fell at the same time.
Yeah, I think it would have stopped. So you gamed the system.
Did I game the system, or did I just partake in
Was
my
protecting the
natural?
system?
Did you steal?
Okay, the way that, what we're going to do is, we studied where we came up with equations of motion by discretizing the system in these little masses connected by springs and dampers. We're now going to look at, sometimes you can actually do a better job modeling the system by representing it as an actual continuous system as it truly is, right? Like this beam. Instead of breaking up into little masses and springs, let's treat it as a continuous model, like we might do in mechanics of materials. Okay? So what I've drawn here is, I didn't put any boundary conditions at the end. I've left that generic for now because that's what's going to change the problem. The problem's actually, once we get to the equation of motion of this beam, what's going to change the dynamics is going to be whether it's fixed at one end, free at one end, or pinned at one end. Okay, it's the boundary conditions that really influence the dynamics between this beam that's just, free. The fact that it's sitting on a foam is simply to isolate it from what it's being supported on, and one that might be clamped at one end where it's, cantilevered. Right? And 2 things I want to point out about the experiment. When you run this experiment, I strongly suggest running your test in 1711 on those tabletops in there. They're much more rigid than these tables, and you want to test on a rigid surface because you don't want to pick up the dynamics of that rigid surface. Okay? Because remember, the accelerometers are going to pick up any vibration, right? Be it the beam or anything else that's connected to the beam. So if you test on a very rigid surface, like in those tables in the lab, you're going to get much better measurements. The other thing is the key for the cabinet will be in Andrea's office, which apparently is always unlocked. I don't know if that's a hidden secret of what, but I guess you guys know that.
Yeah.
And she will keep it on her little tray for her whiteboard. So it'll be there, so you can get it from there, unlock the cabinet, but after you put the stuff away, lock the cabinet and put the key back so the next group can get in there.
Is there only one cabinet in there that's locked?
No, but the cabinet is labeled 621.
Okay.
I think there's actually 2, I'm not sure if there's 3. One of the cabinets has been moved down here. There may be only one other cabinet.
Did you?
You said 621.
It's labeled 621 and there's a few other things in there as well, but they're not. There's a box of cables. There's a bag that contains all of these guys, and this guy will be in there. That's the only thing that you guys are going to be interested in, except in the data acquisition system will be in there as well. Okay, so what I have is some generic beam. I haven't really indicated what the boundary conditions are going to be yet. We'll talk about that later when we go through an example. It's got, just to keep the problem very generic, it's got a distributed load that's being applied onto it in positive upward, all right, in the positive upward direction. And I've drawn it squiggly like that because it might have a different amplitude here, than here, than here, than here, and here. So it's a function of x, that distributed load, but it's also dynamic. So it's a function of time as well. All right, so unlike mechanics materials, we're going to actually include the actual dynamics of what's going on with the beam, not just the statics, all right, like we would do in MOM. So to get the equation of motion, we're actually going to get one single equation to describe the motion of this beam. It's going to be a partial differential equation, which will be a function of both space and time. Because if we're placing an accelerometer here, it's going to be different than when we place an accelerometer here, right? The vibration will be. And of course, it's time dependent because the force being applied is temporal, right? So I'll cut away a little piece of this beam, right? And so I've got just a little bit of the distributed load acting across there. And of course, with breaking that out, we have to include the internal shear force on this surface and the internal shear force on this surface. And the little piece I cut out is of thickness delta x. So the shear forces are a little different from one another because one's being applied on the left side at x and one is being applied on the right side at x plus delta x. And then there's a moment acting on this side at x, and there's a moment acting on this side at x plus delta x. And of course, all of these internal variables are also a function of time as well because of the fact that the force being applied is dynamic. Now, this beam is deformed somewhere above, this element is deformed somewhere above static equilibrium an amount y x plus, or x t. Okay. Now, this is an Euler beam model. You guys might ask, well, what about the fact that this might twist, and so this end might be a little higher than this end? The assumption here is that this delta x is so small that the deformation, how much this side of the beam is up from this side, is negligible. Okay, and if you get into there's some other beam models out there that are a little bit more complex that take care of rotary dynamics, actually rotational inertia taking place, that are called Timoshenko beams. Okay, Timoshenko is a guy that came up with a little bit more involved model. We're going to do what's called the Euler beam model, right, which is a little bit more simplified. Does everybody understand this free body? Okay. Okay, so this end is at x. Just making sure I get all the details. And this end here is at x plus delta x. This end here, which is, I don't want to make this too busy. The beam has this isn't density, all right? I know rho typically is used as a variable for density. This is actually mass per unit length. And it is this beam could be non-homogeneous, so therefore the mass per unit length, hence the density, could vary along the length, right? And likewise, when you take the area moment of inertia, I, and the modulus together as a single product, that's called the flexural rigidity of the beam. And together they could both vary, right? This could be a tapered beam so that the area moment of inertia is different along it. And again, because it could be non-homogeneous, it might have a varying Young's modulus as well. So that together could be a function of x. So what we'll do now is we will sum the forces in the y direction, okay? So y being vertical, positive motion being defined as upward. And this is a dynamics problem, so sum of the forces is not equal to 0, but is equal to mass times acceleration, right? So what is that? What is mass? What is the mass of this element?
The length time
Rho times x.
delta x.
Yeah, right. It'd be rho x times delta x. That takes care of the mass part. And what is the acceleration?
X double dot?
Well, we're not using x for displacement here. X is in this problem is the measurement along the length of the beam.
Is it wide open?
Yeah, and we have to be careful of the derivative because y is not just a function of time, it's a function of space. So we got to use a partial derivative, right? So it's the partial of y, which is a function of both x and t, with respect to t squared, right? So there's mass times acceleration. And that's equal to, well, we got all these different forces taking place. We've got v of x plus delta x t minus v of x at t plus f at x at t times delta x, because that's a mass. This is a distributed force, so it has units of like newtons per meter, right?
Sorry, can you describe what that is again?
Which one? This?
Yeah.
This? Well, we're summing the forces.
Oh, okay.
So we've got the shear on the two ends, and then we've got the distributed load. I should have labeled this. This is f of x at t times delta x, right? Because it's a mass, it's a force per unit length. And likewise, we'll take the sum of the moments, and we're going to, when you take the sum of the moments, you have to specify where you're taking the sum of the moments about, right? So we're going to take it at x, at this end here, okay? And we're not including, I already mentioned earlier, if this were a Timoshenko beam, something where we're going to include rotational inertia. This wouldn't be equal to 0, but in this simple Euler beam problem, we're going to assume that the rotational inertia is 0, all right? So the sum of the moments are going to be equal to 0. And that is, m at x plus delta x t minus m x t, and then also we have the shear on this side times its moment arm, so plus v x plus delta x t times dx, and then plus, we still have the external load that's being applied, right? And what we're going to assume is that because this is a very small infinitesimal piece, right, that even though this distributed load may vary in amplitude going along here, over this very small portion it's constant. Okay? So that would be, is that plus? That's actually, yeah, plus, because it's acting upward. F of x t delta x, now that's the force, and then we need the moment arm, right? So that's multiplied by delta x over 2. Does everybody understand that? Because the centroid, if this is assumed to be constant, the centroid's right in the middle, right? All right. Now, what we're going to do is apply a Taylor series expansion of first order Taylor series. Okay, and that is that we can write m of x plus delta x t equal to m x at t and t, m of x and t, plus the partial of m x and t with respect to x times delta x. Does that look familiar for a partial Taylor series, first order Taylor series? I think you guys are used to you guys have probably, if I wrote this, you guys know that f of x plus, or x naught, right? X plus x naught is equal to f at x naught plus the partial of f x with respect to x delta x, right? That's a first order Taylor series expansion, right? So that's this equivalent. We're not taking the Taylor series expansion with t, but because we're perturbing x by some small amount, we can write it as that. And the same holds true for the shear. V of x plus delta x t is equal to v x t partial v